Hi, and welcome to assignment 5. In this assignment, we'll be focusing on how to configure the op-amp in MCC and how to translate from MCC to a Mindi simulation. The objectives are to understand how to configure an op-amp in MCC, configure the op-amp peripheral as an instrumentation amplifier, plot the input and output from the instrumentation amplifier in the data visualizer, and simulate the instrumentation amplifier in MPLAB Mindi. So first, let's talk about the instrumentation amplifier. The instrumentation amplifier amplifies a differential signal and transforms it into a single-ended signal. In addition, it has two very high impedance inputs. All of these qualities make it ideal for instrumentation amplification, as the output of an instrument is often a weak differential signal and a high input impedance is needed to not disturb the measurement. The instrumentation amplifier consists of two op-amps that are configured as voltage follower, here OP1 and OP0, and a third operational amplifier, in this case OP2, configured as a differential amplifier. So OP2 will amplify the differential signal created by the two voltage followers. Let's take a look and see how we can configure this in MCC. So I will press the MPLAB Code Configurator open to open the MCC configuration. And here we can see all the peripheral that I used in this example. And exactly as for assignment 3 and assignment 4, we'll use the DUC to create a sine input, and we'll use the ADC to measure the output of the instrumentation amplifier. Let's take a look and see how we configure the op-amp. So here you have the main system overview for the operational amplifier. We can see that we can enable the op-amp peripheral. We can also set the input range. We'll be using the full range, but we could reduce it if you want to save power. We can see that the time base is automatically calculated for us based on the set clock speed of the device. And down here we have select mode. And here we can select if you want to have a single op-amp, if you want to have dual and single op-amps, or triple op-amps, exactly as we could in start. So we want to have a triple op-amp configuration, as we need all three combined to create an instrumentation amplifier. And we will select the instrumentation amplifier. And down here we can see that instrumentation amplifier can only be created if we have OP0, OP1 and OP2 together in this configuration, which is why this field is grayed out. So let's look at OP0, and as in start, here we will get an illustration showing how this configuration is created, and this dotted line highlights which op-amp you're currently configuring. So we can select the positive input, and for this example, we will set this to VDD over 2, and then we see that all the other fields are grayed out. And this is exactly the same as for start, where the grayed out fields mean that we cannot change them, as this would break the configuration, but are still visible to us for learning purposes. We also have this system gain, where we can set the gain of the instrumentation amplifier. As the gain of the instrumentation amplifier is combined by the resistor of both OP0 and OP2, we will use the system gain to configure the resistor ladders for both of those op-amps simultaneously to give us the gain that we want. So for this example, we want a gain of 3. And down here we have some more advanced hardware settings that we will also familiar with from previous examples. We can run it in standby mode. We can set the output driver. We will use normal as always. We can enable it so it's always on. And we can set a settling time, which once again will set to the maximum. For OP0, we see that the only really meaningful field is the input, which will be the DAC, because the system gain is the same system gain that we configured earlier, and we have exactly the same settings down here. And for OP2, we have no configurations that are meaningful, because the system gain is already set, and everything else has to be exactly as it is. So let's flash this onto the device to see how it looks in the data visualizer. So as always, we start by loading the workspace. This is assignment 5. We have to set up the user communication. And we have to select the right source for the decoder, and then we will show live data. And when we post this, we can see that down here is the differential signal, which is the input to our instrumentation amplifier. And at the top here, we can see the output. And we can see that output is 3 times larger than the input. Now let's say you have created this model, but you want to have a look at it and see how it looks in simulation. We can do this by pressing the Mindi schematic, which will take us to this GitHub page. And as we did previously in assignment 4, we can press release, source code, and we will get a zip, and we can extract this zip and go into schematics to find the schematic. And here we can see 3 op-amps modeling the AVR DB op-amp configured as an instrumentation amplifier. And we want to have a gain of 3. So if you look in this table, we can see that that means that the resistor for OP0 should be 48K and 16K, which they are. And the resistor for OP2 should be 16 and 48K, which they also are, which means that this instrumentation amplifier is configured the same way as our MCC, and we can easily create a simulation. As expected, we can see that the output is 3 times larger than the input, exactly as we showed in the data visualizer. That's it for assignment 5. Thanks for watching.